Good morning to you all once again. My name is Arnold Young and I welcome you all back to the YouTube channel. We've already started a lecture series on single variable calculus, and this is the second lecture. In the first lecture, we touched on limits. We talked about some of the limit rules for evaluating simple limit expressions, and today we begin from where we started the last time. So yes, I would want to include some limit rules. The rule I want to talk about now is the nth rule. Now, what is the nth rule saying? If you have the limit as x approaches some constant of the nth of some function, this limit can be written as the nth root of the limit of f of x as x approaches a. That is the nth root, the nth rule, sorry. Now, when you have the limit of a compound trig function, of a compound trig expression, say cos x plus k, this limit can be written as cosine of the limit as x approaches a of x plus k. I believe these are quite self-explanatory. Yes. So we are done. But in the last lecture, if it is the first time you are joining, we talked about sum rule. We talked about difference rule. We talked about quotient rule. We talked about constant multiple or multiplier rule. We also touched on, we touched on a few rules, but then as we move along, we are going to recap all of them and apply them as well. Now, let's solve some problems applying these rules. So solving problems applying the limit rules. Now, the first we'll be solving is, say you have limit of, say, x plus 2 as x approaches, say, 2. Now here we can apply the sum rule because we have two functions summing up together. We have a linear function and we have a constant function as well. So this can be written as the limit of x as x approaches 2 plus limit of 2 as x approaches 2. Now, what do we get? Here we will just do a direct substitution. So as x approaches 2, then the limit of x becomes 2. Now for here, we have the limit of a constant, and the limit of a constant is 2, regardless of some variable approaching some value, right? The limit of a constant is the constant itself, regardless of some variable approaching some value. So the limit of 2 as x approaches 2 is 2, is the constant itself. So here we get 4. Now let's just say have another example. Say limit as x approaches 2 of x cubed minus 4. We'll have limit of x cubed as x approaches 2 minus limit of 4 as x approaches 2. Now for here, the first one, we can just do a direct substitution. So we'll have 2 raised to the power 3 minus, as I said, the limit of a constant, the constant itself. So a limit of 4 as x approaches 2 is 4. What do we get from here? 8 minus 4. And we have 4. This is quite simple. Now, let's say we have two expressions multiplying. So x plus 2, x plus 3, which is equal to, say, f of x, and been asked to find the limit of f of x as x approaches some constant. It's the same as saying the limit as x approaching some constant of x plus 2, x plus 3. Now here we can apply the product rule first, then we continue. So we can say limit of x plus 2 as x approaches 2 multiplying limit as x approaches 2 of x plus 3. And this gives us now from here we can also apply the product rule. From here we can apply the product rule. So we can have limit x as x approaches 2. I mean the sum rule, sorry, it's actually the sum rule. We are applying the sum rule because we have x plus 2. Here we also have x plus 3. So the limit of x as x approaches 2 plus the limit of 2 as x approaches 2, all in parentheses, multiplying the limit of x as x approaches 2 plus limit of 3 as x approaches 2. Now for here, for the first one, we can just do a direct substitution. So 2 plus, as I said, the limit of a constant is the constant itself. So 2. Here we can also do direct substitution. We have 2. The limit of a constant is the constant itself. 3. So we have 4 multiplying 5. We end up with 20. Now, let's say you have the limit as x approaches, say, 3 of 2x cubed plus 4 divided by 3x squared plus 3. Then this can be written as limit of 2x cubed plus 4 as x approaches 3 divided by, we are applying the quotient rule, limit as x approaches 3 of 3x squared plus 2. Now for the first part, we can apply the product rule there. So limit of 2x cubed as x approaches 3 plus limit of 4 as x approaches 3, all on limit as x approaches 3 of 3x squared plus limit of 3 as x approaches 3. And this becomes, for the first one, you realize there is 2 here, which is a constant. You can move inside and out of the limit. So I can write this as 2 limit x cubed x approaching 3 plus the limit of a constant, the constant itself. So 4 divided by, you can do the same thing for here. We have a constant here. You can move inside and out of the limit expression. So we have 3, the limit of x squared as x approaches 3 plus the limit of 3. Since 3 is a constant, the limit of 3 is 3, regardless of any variable approaching some value. So what do we have? We can get from here, we can do direct substitution. X approaching 3, so substituting 3, we'll have 2 multiplying 3 raised to the power 3 plus 4 divided by 3 multiplying 3 raised to the power 2 plus 3 because we have x squared here. So you can just do direct substitution. So what do we end up with? 3 times 3, 27 times 254 plus 4. We have 9 times 3, 27 plus 3. So we have 58 over 30. Now let's just say we have another limit. So say you have the limit of the third root of the expression s squared plus 2 as x approaches 4. How can we write this? We can write it as the third root or the cube root of the limit. We are applying the nth root rule, right? The nth root rule. So x approaching 4 of the expression x squared plus 2. We end up with what? The third root of limit of 6x squared as x approaches 4 plus multiplying the product rule within the root, the limit as x approaches 4 of 2. So this becomes simple. We have 6 here, which is a constant. You can move inside and out of the root expression. So we have 6 multiplying the limit as x approaches 4 of x squared plus, now the limit of a constant, as I said, is the constant itself. So what do we end up with? The third rule of 6 multiplying 4 squared plus 2. 4 squared is 16. 16 times 6 is, I think, 216, or 16 times 6 is 216 plus 2. End up with cube root of 218. Oh, sorry. 16 times 6 is not 216. It is rather 96, sorry. So 96 plus 2 is equal to third root of 98. So I think we've touched on almost all there. Now let's go to the next one. Say, I think I didn't talk about this, but let's say you have the limit access approaches 3 of, say, log s cubed plus 6. This can also be written as log of the expression limit as x approaches 3 of x cubed plus 6. Then we apply the limit rule. Can apply the sum rule here. So we'll have limit of x cubed as x approaches 3 plus limit of 6 as x approaches 3. And now here we can do a direct substitution here. So we have 3 raised to the power 3 plus limit of 6 as x approaches 3. Since 6 is a constant, then the limit of a constant, the constant itself, end up with log 3 raised to the power 3 is what? 3 raised to the power 3 is 27 plus 6, so we end up with log 33. Now, though we are not talking about limits of trig functions now, but I want to include this example. So let's say you have the limit of, say, cos s cubed plus 6 as x approaches 10, say 10 degrees as x approaches 10 degrees. Can also do the same thing, right? So I will leave this to you. Try this. Try this one. Now we move on to the next concept to be understood. Let's talk about let's talk about the limit of rational expressions or rational functions. A limit of rational functions. Now, what then is a rational function? Say you have functions, say you have function fx and g of x, and let's say they are all polynomials, right? Now, h of x is equal to, say, f of x divided by g of x, where g of x is not equal to 0 because we want our function h of x to exist, right? We want our h of x to exist, so g of x, which is the denominator, shouldn't be 0 because when it's 0, then the whole h of x becomes undefined. It approaches infinity, we cannot define the exact h of x function. So yes, if you have f of x divided by g of x, where h of x is equal to f of x divided by g of x, then our h of x becomes our rational function. That is it. It becomes our rational function. So that's how to define rational function. Now, let's find the limit of a rational function. Say h of x, as we defined, is equal to f of x divided by g of x. Finding the limit of h of x, so the limit of h of x will be what? Now from here you realize the limit of h of x will be limit of f of x, say as x approaches some constant a, over g of x as x approaches a. I can apply the limit rule. Can apply the quotient rule here. So what is the quotient rule saying? It will be limit of f of x as x approaches a divided by limit of g of x as x approaches a, which will be limit as x approaches a of h of x. For here, we can do direct substitution, right? So for the direct substitution, limit as x approaches a of h of x would be f of a divided by g of a. Oh, then we can say that then for limit of h of x as x approaches a, it will be the same as h of a. As simple as that. And I think this is self-explanatory because see, we had h of x being equal to f of x divided by g of x. Now to find the limit as x approaches a, what do? We can apply the limit rule, the quotient rule. So we find the limit of the numerator separately, divided by the limit of the denominator separately. Now, what do we do then? We can now substitute in what? The value we are approaching, which is a. So limit of f of x, then it will be f of a divided by g of a. So the limit of h of x as x approaches a will be f of a divided by g of a. And since x is a, then I can say that, oh, the limit of h of x as x approaches a is the same as h of a. And I believe this is quite self-explanatory. Yeah, this is so simple, right? It is so simple. So let's draw some basic conclusions. So if you have a function f of x, g of x, or say h of x, then the limit of f of x as x approaches a is f of a. You can just do direct substitution. The limit of g of x as x approaches a is g of a. Just direct substitution. The limit of h of x as x approaches a is equal to h of a. Just direct substitution. Mind you, there's one thing I want to tell you. Whenever, for every limit expression, if the limit laws are applicable, then you can do direct substitution. We'll talk about that. Now, so let's say you have, I want to give an example. So example, you have, say, limit of 2x cubed plus 3x plus 1 divided by 5x plus 4 as x approaches 3. It is simple. You just have to do direct substitution. But first, let us apply the limit rules, right? Then after we do direct substitution, you realize they are both the same thing. So applying the limit rule, what are we going to get? We're applying the quotient rule first. We have limit of 2x cubed plus 3x plus 1 divided by 5x plus 4. So this becomes limit of 2x cubed plus 3x plus 1 as x approaches 3 divided by limit 5x plus 4 as x approaches 3. So from here, for the numerator, we can apply the sum rule. So we can say limit of 2x cubed as x approaches 3 plus limit of 3x as x approaches 3 plus limit of 1 as x approaches 3, all divided by limit of 5x as x approaches 3 plus limit of 4 as x approaches 3. So here the job is done. For the first expression, since we have 2 in the limit expression, 2 is a constant and 2 can move inside and out of the limit expression. So you can write that as 2 multiplying the limit of x cubed as x approaches 3 plus, the same applies to the next term, right? We have 3 as a constant, can move out the limit expression as x approaches 3 plus the limit of a constant is always a constant itself. So I have 1 divided by, we can do same for the denominator, 5 the limit of x as x approaches 3 plus limit of 4 as x approaches 3 is a constant itself, which is 4. So what are we going to have? 2 multiplying 3 cubed plus 3, 1 divided by 5 multiplying 3 plus 4. What do we end up with? 3 cubed is 27 times 2, 54 plus 9 making 63 plus 1, 64. 5 times 15, 4, 19. So we end up with this. As I said, you can also do direct substitution. It will also work. Now, so for the direct substitution, limit as x approaches 3 of 2x squared plus 3x plus 1 divided by, wait, I'm coming, let me check. Okay, it's actually 2x cubed plus 3x plus 1. 2x cubed plus 3x plus 1 cube plus 3 divided by 5x plus 4. Okay, I'm sorry. Can do direct substitution. So as x approaches 3, then 2, this expression becomes 2 multiplying 3 raised to the power 3 plus 3 times 3 plus 1 divided by 5, 3 plus 4. So what are we going to have? We are going to have 3 raised to the power 3 is 27 times 2, 54 plus 9, 63 plus 164 divided by 5 times 3, 15 plus 4, 19. So realize it's actually the same. So for every limit expression, if the limit laws are applicable, then you can do direct substitution. I believe this is quite understandable. Let us try another example. So say you have limit x approaches 4, 2x cubed minus 5 divided by 3x plus 2. How do we solve this? Let us apply the limit rules first. So this can be written as the limit. We are using the quotient rule first. So for the quotient rule, find the limit of the numerator first, divided by the limit of the denominator as x approaches 4. What are we getting? We end up with, for the numerator, we can apply the difference rule. So limit of 2x cubed as x approaches 4 minus the limit of 5 as x approaches 4 divided by the limit of 3x as x approaches 4 plus limit of 2 as x approaches 4. What are we getting? So for the first one, there's a constant here, can move inside and out of the limit expression. We have 2 multiplying the limit of x cubed as x approaches 4 minus the limit of 5 as x approaches 4 is the constant itself. So it is 5 divided by, can do same for here. There's a constant here, can move inside and out of the limit expression. So we have 3 limit of x as x approaches 4 plus, now we have the limit of a constant. The limit of a constant is a constant itself. So now for here we can do a direct substitution. So we have 2 multiplying 4 cubed minus 5 divided by 3 multiplying 4 plus 2. Then what do we get? 4 raised to the power 3 is 64. 64 times 2, 128 minus 5 divided by 3 times 4 is 12 plus 2, 14. End up with 123 divided by 14. As I said, we can also do direct substitution. So by direct, without applying the left, so by direct substitution. So as x approaches 4, then the expression becomes 2 multiplying 4 minus 5 divided by 3 multiplying 4 plus 2. End up at 1, 2, 3 divided by 14. Yes, as simple as that. I think this is quite self-explanatory. Let's move on to the next concept to be understood. Now, I want us to talk about the indeterminate form of a rational function. If you say some rational function is indeterminate, what does it mean? Now, let's say a rational function h of x is equal to f of x over g of x, right? Now, for h of x to be indeterminate, then f of x should be 0 and g of x should be 0 as some value of what? X. And mind you, f of x and g of x are all polynomials. F of x and g of x are all polynomials. And if f of x is 0 and g of x is 0 at some particular value of x, then our h of x is indeterminate. Our h of x is indeterminate. So for an indeterminate function, we end up with 0 divided by 0. This is the basic understanding of indeterminate. Now, for indeterminate limit expressions, there are a number of ways of evaluating them, right? So we'll begin them with some examples, then we continue. Now, let's just say you have the limit of some expression. So the limit of x squared minus 3x divided by 2x squared minus 5x minus 3 as x approaches 3. Now, let us try to do direct substitution. So by direct substitution, what do we get? We end up with 3 squared minus 3 times 3 divided by 2 multiplying 3 squared minus 5, 3 minus 3. Now, what do we get? 9 minus 9. And the denominator will be 2 times 9, 18. And negative 15, negative 3 is a negative 18. So we end up with 0 over 0. So that is an indeterminate form of a limit expression. So for now, since we've realized it is indeterminate, then there are a number of techniques for evaluating them. But then I want to talk about, that is the steps for evaluating indeterminate form of limits, or let me say procedure. Indeterminate form of limit. So the first procedure. Now, if the limit function is, or let me say, if the function want to find the limit, right? After doing a direct substitution, it's made up of polynomials, right? So let's say f of x over g of x. Then what do? You try as much as possible to simplify by factorizing to cancel out the factors. So first, simplify by factorizing. To cancel out all the factors as possible. Now, the second step or the second procedure I want you to consider is if the numerator and the denominator have square root, then what do? You rationalize either the numerator or the denominator. So the second one, if the numerator or denominator have square root, then rationalize the numerator or the denominator. Now, the next one is for complex fractions, simplify first. So for complex fractions, after realize it is an indeterminate form, just simplify first. Then after applying all this procedure, then you can apply the limit rule. But if the limit rule is applicable, then you can do direct substitution, right? Yeah, so we take a few examples for us to get to the understanding of what we are talking about, right? So the first example I want to talk about would be, let's say you have the limit x as x approaches 3 of say x squared minus 3x divided by 2x squared minus 5x minus 3. But mind you, whenever you are given the limit expression, make sure you do the direct substitution first before you can apply the procedures for solving an indeterminate form, because you have to check whether the limit expression is an indeterminate one or not. So here we are checking, we are doing direct substitution. So as x approaches 3, what do we get? We'll have 3 squared minus 3 multiplying 3 divided by 2, 3 squared minus 5 multiplying 3 minus 3. What do we get? 9 minus 9, which is 0. The denominator 2 is also 0. So this is an indeterminate limit expression. So what do? We try to do what? To simplify. But then you realize the numerator is a polynomial. The denominator is also a what? A polynomial. So what can we do? We factorize, right? We factorize to cancel out as possible. Then we can continue to apply the limit rules or do the direct substitution. So limit as x approaches 3. Here we can factorize the numerator, can factorize x out. So x out, we end up with x minus 3 divided by, for the denominator, right? It is a quadratic expression. So we have to factorize. To factorize this quadratic expression, let us factorize it somewhere. What do you think this will be? Now for this one, 2x squared minus 5x minus 3. 2, you multiply the coefficient of x squared by the constant, right? That's the last term of the expression. What do you get? We get negative 6. Factors of negative 6, that's when multiplied will give you negative 6, but then when added will give you negative 5. Will be, what do you think? Will be 2x squared minus 6x plus x minus 3. So you realize the factors are what? Negative 6x and x, right? Negative 6x and x. So here factorizing, we end up with 2x out, x minus 3 plus 1, x minus 3. So 2x plus 1, x minus 3. So these are the factors of the expression 2x squared minus 5x minus 3. Now, so we can put it in there. So limit as x approaches 3, x multiplying x minus 3 divided by 2x plus 1 multiplying x minus 3. So from here, we can actually cancel out some of the expressions. So we can cancel out x minus 3 here, x minus 3 here. End up with limit as x approaches 3, x divided by 2x plus 1. Here we can do direct substitution. Then what do we get? As x approaches 3, we end up with 3 divided by 2 multiplying 3 plus 1. 3 divided by 2 times 3, 6 plus 1, 7. The 3 over 7 is our answer. Now let us try another example and see if we have an understanding of what we are doing. Now the next example, say you have limit as x approaches 2 of x cubed minus 7x squared plus 10x divided by x squared plus x minus 6. Now, we can also, since the numerator and the denominator are both polynomials, then what do? We try to factorize the what? The expressions on the numerator and the denominator. Then we cancel out some of the what? Some of the factors. So yes, this becomes limit as x approaches 2. We can factorize the top expression, right? We can first factorize out x. What do we get? X squared minus 7x plus 10 divided by x squared plus x minus 6. Now, so we have limit as x approaches 2 of what? We can factorize x squared minus 7x plus 10 again. So we'll have x multiplying x squared. Coefficient of 1 multiplied by 10 is 10. Factors of 10. Now when multiplied will give you 10. But then when added will give you what? Negative 7. Right? Or there will be negative 5 and negative 2. Right? When negative 5 and negative 2 are multiplied, you get 10. When they are added, you get negative 7. So negative 5x minus 2x plus 10 divided by, let us factorize here. Here we end up with x squared plus 3x minus 2x minus 6. So limit as x approaches 2 of x multiplying, here we are simplifying, multiplying x out, end up with x minus 5. Here factorize the negative 2 out to end up with x minus 5. Here factorize x out, end up with x plus 3. Factorize negative 2 out to end up with x plus 3. So the limit as x approaches 2 of x multiplying x minus 5 in parentheses, multiplying x minus 2 in parentheses, divided by x minus 2, x plus 3. So from here we have limit as x approaches 2 of x, x minus 2, x minus 5 divided by x minus 2 x plus 3. So you realize you can cancel out some of the expressions. X minus 2, x minus 2 is out. Then we have limit as x approaches 2, x minus 5 divided by x plus 3. So as x approaches 2, we end up with 2 minus 5, 2 plus 3. Then we have negative 3 divided by 5. I think this was actually a nice example. Let us solve another example on this, then we end the class. Then in the next lecture, we continue with solving indeterminate limit forms where we have square roots or radical expressions in there. Okay, so let's take this expression. Another example, limit of x squared minus 5x plus 4 divided by 4x squared plus 2x. Let me see. Okay, so I'll do one thing. I'll give this to you for you to try on your own. Okay, I'll give this to you for you to try on your own as x approaches 0. So this is an assignment. We end the class here. We'll meet in the next lecture where we will solve problems on indeterminate forms of limit expressions with square root or radical expressions. Thank you.